Okay, so good morning. Let's start immediately. So last week we basically obtained a linearized version of the 6th degree of freedom equations of motion, right? So we basically obtained an A matrix. It looked like this. It's kind of confusing now. We did a lot of work here. And a control matrix. So if you would consider this to be the states of the aircraft, what we really obtained was a set of differential equations, linear differential equations that look like this, right? X dot is equal to AX plus BU, right? Where X is basically the state variables, A is the matrix, and B is, again, the control matrix. And U being the controls, right? You are the controls. In our case, it's the pilot controls. The way we represent the pilot controls at this point is by just adding forces and moments that are generated by the pilot. So they can be generated by the aileron, by the thrust, by the elevator, whatever, but at the end, they generate some forces and moments. And we call them controls now in this case, okay? So this one being the system matrix, it's an A matrix. The A matrix is an 8 by 8 because the number of states that we have are 8 states. If you look at the first 4 states, I arranged them such that we can divide them into longitudinal and lateral dynamics. Here you have the longitudinal, U, the body x velocity, W, the body w velocity in the z body direction, the velocity, Q, angular rate, delta theta is the geometric pitch angle, and so on and so forth, right? So here you have the lateral and the longitudinal. And what we discovered also is that because we made that distinction between longitudinal and lateral dynamics, basically saying that the lateral will not affect the longitudinal and the longitudinal not the lateral, you see that we have a bunch of zeros on this quarter of the matrix and a bunch of zeros here on this quarter of the matrix, because the effect of the lateral dynamics onto the longitudinal dynamics is basically 0, but that's an assumption we made from the very beginning. And the same thing over here, the longitudinal has no effect on the lateral, therefore you have all these zeros. As a result, if you look at this A matrix, 2 quarters have numbers in there, and a bunch of them doesn't have any numbers, right? So it has numbers, but there are zeros. So what you could really do is you can separate the longitudinal from the lateral dynamics, and then analyze the lateral dynamics by itself, and the longitudinal dynamics by itself, okay? So you don't have to do it all together. If you had a lot of numbers over here, basically if there were a lot of cross-coupling between those two between the longitudinal and lateral dynamics, you could simply just look at the whole matrix. But as I said, for fixed-wing airplanes, the coupling between the longitudinal and lateral is quite minimal, okay? It's not very large. If this was a helicopter or maybe some other flying object where this is not 0, then you have to really do an analysis on the whole thing. But since these are zeros, we can really separate them into longitudinal dynamics and lateral dynamics, 2 different dynamics which don't affect each other, okay? So that means we can actually take this part and say this is now the longitudinal dynamics. So basically I could write simply that, right? I could write del dot w dot q dot and delta theta dot is equal to A long, which is this part, which is the 4 by 4 of this A matrix, times again del u w q delta theta plus the B matrix of the longitudinal dynamics, basically just this part, the top part here, just this part, okay, times del xc, del zc, and del mc. Okay? This is how this whole thing would look like. And this would be a 4 by 4 matrix, this one here. This one would be a 4 by 4 matrix, right? Because it has only the longitudinal dynamics. You could write, and this would be the longitudinal dynamics. Okay? And now you can write a very similar thing for the lateral dynamics. We could write for the lateral dynamics, we could write a very similar thing. We could say now, V dot, R dot, P dot, and phi dot is equal to A, now call it the lateral dynamics, A lat, and here we have V, R, P, and phi. Okay? And that's again a 4 by 4 matrix. Plus B lat, lateral dynamics, and here you have the rolling moment coming from the control, basically from the pilot, delta y coming from the pilot, and delta nc again coming from the pilot. And this one we would call the lateral dynamics. So what is A long and A lat? It is basically these parts here. This part here of the 8 by 8, this part would be A long, okay? This would be A long. And this part of the A matrix would be A lat. I mean, basically the lateral dynamics of the 6 degree of freedom equations. You see? At the same time, B long would be somewhere here. This would be B long, and the last 4 here, that would be B lat, basically the lateral dynamics. So if you take this A long, the lateral dynamics and the longitudinal dynamics, they start looking like this. Does that make sense? Do you have any questions here? So let me show you how the full matrix look like, because we didn't really, I hope this will work. What this A long and A lat really look like, I can quickly, I think we should be able to show it to you from here. Okay, there you go, wonderful. So, this is the longitudinal dynamics. I mean, this is from the Etkin book in edition 1996. The Dynamics of Flight, Bernard Etkin, okay, 1996. You can have this in any book. So, this here is the 4 by 4 matrix. Look at the states. It's delta U dot, W dot, Q dot, and delta theta dot. So, and here you have the 4 by 4 matrix, you see, the one I just wrote. And the first line, look at the first line. This is the one we obtained last week. XU, which is basically del X del U divided by M. That's the first term over here, you see. The second term is del X del W divided by M. And then you have the 0, and then you have minus G cosine theta. This is the first line we obtained last week. Do you remember that? Right? And then if you want to do the rest, you know, the W dot, the Q dot, the theta dot, you obtain all these different terms. And look at these terms. You have M minus ZW dot, right? ZW dot is del Z del W dot, right? And then here you have mw, right? Del m, del w. And you have all these terms. So some of the terms look a little bit more complicated, especially the one with the rotational dynamics. But you see that it is a 4x4 matrix, right? You see that? Right? And here you have the controls. It's a little bit more involved, the controls, but really doesn't matter. You still, it is just a B matrix, and the controls are written in one piece. But we are really interested in this matrix here. Because when we write this matrix, then we can look at the stability of this aircraft in the longitudinal dynamics, right? That was a whole goal. And remember, this is still a linearized equation, a linearization around the trim point of the aircraft in steady flight, okay, with wings level flight, okay? And you might, yeah, so that's that. So do you have any questions how this is obtained? And because this is a trim equation, we can also say this is a perturbation equation, right? Every variable is also a perturbation from the trim point, right? We obtained this last week where we first linearized it and then looked at the perturbation equation. We discovered they are the same. So linearization is nothing but having perturbations on each variable. So this would be, for instance, delta u. The reason this is a w is because it is a perturbation, because from the perturbation, if the perturbation point is 0, then there's no need to write delta w, it's just w or delta q, because q0 or w0 is either 0 or we assume it to be 0. Okay? So a very similar thing you can do in the lateral. So the lateral looks like that. See, this is again a 4x4 matrix. And here you see a little bit more complex terms with ixx, for example, is now here. But ixx is really this, ix prime is really a large number. But it is again a function of ix, iz, izx, okay? Assuming that ixy and iyz is equal to 0, this is the 4x4 it would look like. So how difficult is it to obtain these 4x4 matrices for an airplane? Well, it's not really that difficult if you know all these aerodynamic variables. Del y, del p is the partial derivative. What does it mean, partial derivative? Everything is fixed. You're looking at the change of the y force if there's a change in the p, in the roll. So if I change the roll of the airplane, how much moment, L moment, do I obtain? Okay, you take an airplane, you rotate it, and everything else is constant. How much moment do I get in the roll direction? If you know that number, then this is easy. And I told you last time, getting these numbers is not that straightforward. You either need a wind tunnel to test your airplane, or you do some sort of a computational fluid dynamics, where you do everything on the computer and try to obtain these numbers. Or you look at historic airplanes and say, okay, an airplane of this size probably has a del y, del p that is equivalent to this, okay? So you need to go to historic data. And if you have all these, and another thing is also, of course, finding the inertias. Finding the inertias for airplanes are not that straightforward either, because it has a lot of pieces, and there is electronics, avionics, hydraulics. You add everything together and you get these numbers. So this is also not easy to get. Let's say you have it, then you have a 4x4. All you need to do is look at the eigenvalues of this thing, right? You agree? Okay. So here I have a bit of an example. Let me see if I make this bigger. Okay. Okay, this is the 8x8 for an F-16 in steady pull-up. So it is not necessarily the steady-state trim flight that I was telling you about a second ago, but it is again a trim condition during some pull-ups, right? It's trying to go up. So here's the A matrix and here's the B matrix. And if you look at the A matrix, on the top you see Vt, this is the true airspeed, and then you have alpha, angle of attack, and you have theta, and you have q over here, right? And you understand that alpha here, alpha, is replaced by our w. W was the aircraft's velocity in the z body direction, remember? So, and the velocity in the body direction, that w, is sort of equivalent to alpha. If there's alpha, there's w. So this column is basically replaced by alphas instead of w's, but velocity, alpha, theta, and q, you still understand that this part, the first part, is still the longitudinal dynamics. If you look at the second part, you have beta, phi, p, and r, right? And that would be the lateral dynamics, okay? It would be the lateral dynamics. Because beta is a side slip, but side slip is equivalent with the side velocity. So if there's a side velocity, you have a beta, okay? So basically on the first 4 variables are the longitudinal dynamics, and the second 4 variables are the lateral dynamics. And this is the A matrix, okay, the system matrix. Now look at the system matrix. What we discovered, or we made an assumption, saying that this part here, these 2 quadrants, this one and this one, right? Let me pull it down a little bit. Basically this part and this part we assumed to be 0, right? We said the longitudinal and the lateral, they don't affect each other too much. Now look at the numbers. I mean, many of them are really small, you see, and these are real numbers of the F16, so they are small, right? So these are really small. And look at the numbers over here. You have a 32, right? You have 235, you have 0.9, you have 4.6, and all this right here. And look at here, you have nothing really. Everything is really small. I mean, the largest number here is what? It is 10 to the power, no, it's here, 0.02, right? This is the largest number. So compared to these things, this part is really small. And this part is really small. And you can see, even though here in this example, nobody made the assumption of separating longitudinal and lateral, if you calculate it, they turn out to be really small. You see? And that's the assumption we make. We say they are small, therefore we don't calculate them, they're 0. And this would be the 4x4 that we are looking at. It's not 4x4, you have something called power here, that this line we really don't use in our equations. So if you forget about the power line, you just have this part, this 4x4. This would be the 4x4 we are looking at. Or on this side, we are looking at this 4x4 in order to look at the stability in longitudinal and lateral separately. Okay? If you want to look at everything together, you can look at everything together. But since these are really small, they will not affect each other too much. Does that make sense? So the B matrix is here. This is the controls, and you have 4 controls. One is the throttle, very typical. The pilot control, the throttle, how much power you give to the engine. So it's basically your propulsion. Here you have the aileron, right? The pitch up and pitch down maneuver from the aileron. We'll talk about this later in this course. Here you have the elevator. Sorry, the elevator that gives you push down. And here's the aileron, which will give you the roll, right? And here's your rudder at the back, right? 4 controls. So the 4 controls, how do they affect those 8 numbers, VT, alpha, beta? It's written here, right? The throttle here, the first one, the effect of throttle on VT, on alpha, on theta, on Q, and on power. You know, they say it's the power is affecting through airspeed, and so on and so forth. So it's a little bit different than what we do, but you understand the idea. Is that good? Okay. So what we want to do today is we want to, well, I hope this will work now. What we want to do is we want to take an example of a real airplane. Sorry, okay, it was this one. Of a real airplane. So this was the A longitudinal that I was just showing you about, and this was the A lateral. So what we are going to do today is we are going to give a real example of a passenger airplane. And I will give you a long, and we will look at the stability now, right? For a Boeing 747 flying at 40,000 feet with 0.8 Mach, so it's quite fast. Still a steady flight, and wings level Wings level really means phi is equal to 0, so there's no roll, okay? It's a wings level flight. For a Boeing 747 flying at 40,000 feet with a velocity or a speed of 0.8 Mach, and it's a steady flight, so no acceleration, it's in trim, and it's a steady flight. So the A long the numbers look like this. So someone calculated for this airplane, someone calculated all these calculated all these numbers, especially the aerodynamic derivatives, and they look like this. These are all in British units. So 1395 0 minus 32.2. So that's the first line, okay? 0.09055 minus 0.31351 980. Zero, 0, 0, 1, 0. Okay. And the row, sorry, looks like this. W dot, W dot, Q dot, delta, theta dot. Okay? And these are the longitudinal states. Longitudinal states. So what can we do now? Now this is something like this. A long dot is equal to A long and X long plus the controls, right? The B matrix and the controls. We don't really deal with this too much, care about this too much at this point. We are looking at the stability of the longitudinal dynamics. So all we need to do is do what? In order to look at the stability of this aircraft at this flight condition, all we need to do is look at the eigenvalues and then comment on the eigenvalues, right? So we want to look at the eigenvalues of this. So who's going to calculate the eigenvalues? Someone needs to calculate the eigenvalues now. It's a 4x4. Calculating eigenvalues is not that straightforward, right? Okay. For that, we fortunately have a great tool that we are using all the time. It's called Matlab and Simulink. Okay? Matlab does that very easily. You just input these numbers and say eigenvalue, and it gives you the eigenvalues. And this is for the longitudinal dynamics of the Boeing 747. Is that okay now? Okay. So you want to do it in Matlab? Good. And this is how it goes. So that's my Matlab. All right? How many people haven't used Matlab Simulink so far? Oh, never. Well, it's time to start. Okay? In flight mechanics and controls, it is one of the most useful tools. So you got to start sometime. All right? So let me start from the beginning then. Matlab Simulink looks like this. You double click on this, and Matlab will start. It has a lot of great features. One of them is to calculate the eigenvalues. And I think these are our numbers. Are they correct? Can you check real quick? Some of them are rounded off, but they look to be fine. Yeah, they seem to be fine. So these are the numbers that I inputted before the class, of course, so that we don't have to do it here. Okay, otherwise I would take a long time. But the way you input this is, the syntax for this is like this. You need to input this. We would say A long is equal to, parentheses, and then you say the numbers, 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 and you put a semicolon here in order to say that it is a new line, right, a new row, and then you go on and on and on, and at the end you close the parentheses, and you have all 4 numbers in. Okay, so you can try this really at home. I mean, I can say copy and put it over here, right? Enter, and you immediately get this. And when I say now A long, it will tell me what this matrix is. I don't have to say A long. I just made up that number, that name. Okay. So if you want to look at the eigenvalues now, a 4x4 eigenvalues is not easy, right, to calculate by hand. But if you say eig, parenthesis, A long. Okay, you will see the eigenvalues. You ready? You want to see what the 747 looks like in longitudinal flight? Is it stable, unstable? Is there oscillation? Nothing you want to see? Okay, so enter. That's the result. Boom. What is it? Lots of minuses. Is it good or bad? Good. Why? Stable. Everybody loves stability. It's boring. Stability is boring. I'm joking. Of course we like stability. So here's stability, okay? What do you see? What else do you see? What can you tell me now about these numbers? Now we learned a lot about these things. What can you say? Yes, please. It oscillates. Why do we have oscillation? Because of these things, right? Because it's a complex number. It's 0.8875 I. I is a complex variable. So this is a complex number. So it oscillates. There's definitely oscillation. What else can we say? How many pairs do we have? Conjugate pairs. We have 2 conjugate pairs. Obviously, we have 4 numbers, so we need to have 4 eigenvalues, and 2 of them are conjugate pairs. Is one of them faster than the other? In other words, will one of them faster die out than the other one? So if I start the system, one of them will disappear and the other one will still oscillate. Which one would die out faster? This one, right? This one will die out faster because it's a larger number. Remember, it is going to be, if you solve this differential equation for the linear system, it would be e to the power the eigenvalue. So if you put this e to the power, this number, this will die out much faster than this one. This will take a long time, much longer time to die out, right? It has oscillations, and these are the oscillations. So we already made this these analysis at the beginning of the class. But what I'm trying to say is that now we can talk about this airplane and its behavior in steady flight. What's nice about this example is that this behavior is very similar to most fixed-wing airplanes. So if you would do an analysis for a fixed-wing airplane and find the A-long matrix, going through the trouble of finding all these aerodynamic derivatives, okay? You would, most of the time, with fixed-wing airplanes, you would end up with a picture like this, where you have 2 complex conjugates, okay? One of them being much faster than the other one, and this would be the dynamics in the longitudinal. This would be the behavior in the longitudinal dynamics for a fixed-wing airplane. This is very typical for fixed-wing airplanes. That's what I'm trying to say. All right? So you would have 2 complex conjugates, one being faster than the other one, so there will be oscillation. One will be slower, one will be faster. Okay? So please write these numbers down on your notebook, because I'm going to close now Matlab Simulink, and we'll try to analyze these numbers a little bit further and talk about this a little bit more. You got it? You don't have to be very accurate at the end, I mean. Okay, so what were those things? Okay, it's basically the eigenvalues of A long, right? That's what we found. So let me put it down on a paper. We find the eigenvalues of A long. And they look like this. First of all, we had lambda 1 and lambda 2, a complex conjugate, two eigenvalues, minus 0.3711 plus minus 0.8875 j, or I, and another pair of eigenvalues that look like this, 0.072 j. So if you look in the complex plane, they look like this. We have the real part and the imaginary part, right? And what we found is we found really two complex conjugates. One of them is here, and the other two are here and here, okay? And this one here is at minus 0.37, okay? And this one here is at it's much smaller. It's 0.003, right here. So two complex. So two basically roots here. Okay, and as you said, this one here is lambda 1 and lambda 2, and this one here is lambda 3 and lambda 4. So if you look at these ones, they are much faster than these ones. And if you don't know why this is much faster, please go back to the first and second lectures to the first 2 weeks of this class. And as you know, these are all online now. You can listen to those lectures again. And there I'm explaining why this is faster than this one. So this is fast. This will die out faster. This will just disappear faster. So a few observations. They are stable. Right? We call them statically stable. And there are oscillations. Right? Okay. But we can analyze them a bit further. We can say the following. We can make a table. I'm going to make a table now for this. And I'm going to call them modes. Okay? Each of them I will call modes. So eigenvalues lambda 1 and 2, we call them a mode. And then lambda 3 and 4, we call them another mode. So since there are oscillations, I want to calculate the period of these oscillations. Right? How fast do they repeat themselves? I want to calculate the halving time. How fast does the signal halve? Okay? Because there are oscillations and they are converging, they are going back to zero, right? So it really means that if something is converging as a function of time, okay, if a signal is converging to zero, let's say this is the zero line, it's converging to zero, and it is oscillating at the same time, it really means, I mean, if you start at zero, you are at the trim point, right? So nothing will move if you start at the 0 point. If you start somewhere else, then you will converge to zero. So how do you converge to zero at the same time oscillating? You do something like that. You oscillate, and then finally you go back to zero, right? This is the behavior that this means. It is going back to zero, but it is doing that by oscillating. So if you look at the oscillation, so it becomes kind of like this, right? The envelope of the oscillation goes slowly back to zero. So this is what this means. If you start at the trim point, nothing will happen. Only if you disturb it from the trim point, or you don't start from the trim point, it will just oscillate and come back to the equilibrium point. So this is what you are seeing here. Okay? So what I'm really interested in, a few things. One is the period. What is the period of this oscillation? Okay, so you could look at this. Like this is the period of the oscillation. How many times it repeats itself. And then the halving time. So if this is like x, how long does it take? What's the time for it to halve the signal? Okay, let's say it's halved somewhere here. So what is the time required to halve the signal? And when I say halving the signal, I don't mean when it goes through 0. I mean this envelope, the energy of the system. How much does it take time to halve? And then we can look at how many cycles it will take to halve the signal. How many cycles do I have to make in order for the signal to halve the energy? Okay? And then we will give it a name. Okay? Each mode will have a name because most fixed-wing airplanes have these two modes and they have a name in flight mechanics. Okay? I mean, most fixed-wing airplanes will have that name. So, let's give a short break. Okay? We started a little late, so I don't want to make people wait on the other side. Let's just be back here, please, in 5 minutes. Okay? Don't make it 10 minutes. Let's just make it 5 minutes.